So good afternoon, my dear students. My name is Dr. KCH Apparao, working as an associate professor in Mechanical Department, Institute of Aeronautical Engineering, Hyderabad. Okay, in previous classes we discussed the heat exchangers. So from this class, I would like to start radiation topic. Okay, so in this class, I would like to give the introduction of radiation. Radiation. Okay, so this is the third mode of heat transfer. We know that we already discussed this one in first unit. Okay, so you know that what is radiation. So compared to convection and the conduction, so radiation is something different. So for convection and conduction process, medium is very important, but radiation, so no need of any medium for the transfer of heat from one body to another body. You know that these things. Okay, we'll see the once again I want to repeat the introduction of radiation, which was already covered in first unit. You know that so how does heat energy get from the sun to earth? We know this one because sun, there is a lot of gap between the sun and earth. There is no medium between the sun and earth, even though heat transfer takes place from the sun to earth. You know that. Okay, it means there is no particles, there is no medium, okay, between sun and earth. So even though heat is transferring from sun to earth, okay, so it means we can say it is compared to conduction and convection, so it is different because for the radiation, no need of any medium or no need of any particles. So no need of movement of the particles or vibration of the particles, which were placed in conduction and convection. Okay, so without movement of the particles, so radiation takes place and heat transfer takes place by radiation process. We'll see. So we'll see some points regarding the radiation, which were already covered in first unit. So radiation is heat transfer through space. Okay, so no means of any no means of particles, but by means of electromagnetic wave phenomena. It is very important. This topic is already we already studied in physics. You know that. So by means of electromagnetic wave phenomena, other than conduction, convection, we know that. So in conduction, heat transfer by two types of the phenomena. One is the particle vibration or free electron movements. We know that. In convection, it is completely associated with the bulk movement of particles. Okay, but in case of radiation, there is no any medium. There is no need of particles or movement of the particles, but it takes place by electromagnetic wave phenomena. Okay, so unlike conduction and convection, radiation can occur in empty space, no need of particles, as well as in solids, liquids, and gases. You know that in solids, through conduction, heat transfer takes place. In liquids, through convection, liquids and gases also. It means fluids. In fluids, heat transfer takes place by convection. You know that. But for radiation, no need of any medium, no need, just it occurs in solids, in liquids, and gases. Okay, so it is an electromagnetic wave phenomena. So we'll see what is electromagnetic wave phenomena. Okay, so it means no medium is required, no movement of the particles. So waves, you know that. So we'll see what is the electromagnetic wave phenomena. Waves such as we know that visible light and X-rays, ultraviolet rays. Okay. So just alpha rays, gamma rays. You know that so many rays are there. Okay. So we'll see few points regarding the radiation. So radiation travels in the straight lines. Okay. So because if it is sun, radiation moves in all directions, just like okay. So it travels in straight lines. So that is true. Radiation can travel through vacuum. Okay. No need of any medium. Okay. So radiation can travel through vacuum. So radiation requires particles to travel. So it is false because for radiation, no need of any particles or particle movements also. Okay, radiation travels at the speed of light. Okay, so it is uh, radiation occurs by means of electromagnetic wave phenomena. Just like electromagnetic wave phenomena, means it is similar to movement of the light rays. It is also radiation also very equal to speed of the light. Okay, we'll see a few points regarding that one. You know that Stephen Boltzmann law, just like yeah, that was already covered in first in it. It means this law, Stephen and Boltzmann law, explains the just like a concept of radiation, and it gives the mathematical formula for finding the rate of heat transfer through radiation. So, according to this Stephen Boltzmann law, we know that rate of heat transfer is the fourth power of the absolute temperature. So, Q is directly proportional to T to the power of 4. You know that. Okay. So, otherwise, Q is equal to sigma area and T to the power of 4. Okay. So, according to Stephen Boltzmann, you know that radiation energy emitted by body is proportional to the fourth power of the absolute temperature. If there are two bodies like T1 and T2, just temperatures, two bodies, body 1 and body 2, the temperatures of corresponding bodies T1 and T2. If the T1 is greater than T2, so heat transfer takes place from body 1 to body 2. So in this case, just like you know that the formula for the Stephen Boltzmann law, according to Stephen Boltzmann law, rate of heat transfer is equal to F into sigma A T1 to the power of 4 minus T2 to the power of 4. Here F is the view factor. It is depend upon the positioning of geometrical positioning of the plates. Next, sigma, you know that Stephen Boltzmann constant, the value of Stephen Boltzmann constant also already we covered this one in first unit, 5.67 into 10 to the power of minus 8. So watt per meter square, Kelvin to the power of 4. So this value. Okay, just F is the view factor. So this is the just like electrical analog formula. So it means temperature difference by thermal resistivity. This covered in first unit. Just now we'll see just like electromagnetic phenomena. So there are many types of electromagnetic radiations. You know that so in which just like thermal radiation is only one. Okay. So regardless of type of radiation, we say that it is proportional to the speed of light. Okay. So it is proportional to the speed of light. We know that speed of light is equal to 3 into 10 to the power of 8 meter per second. So you know that uh, so you know this value. Okay. You know this formula, just like the speed is equal to the product of wavelength and the frequency. So C is equal to lambda into nu. You know that. So C is the speed of the light and lambda is the wavelength and nu is the frequency. Okay. So this formula. So the units of lambda maybe in centimeters or angstroms. You know that an angstrom is equal to 10 to the power of minus 8 centimeter. So or micrometers also, 1 micrometer is equal to 10 to the power of minus 6 meters. So you know that one. The portion of electromagnetic spectrum. So it is shown in figure. We will see this one. This is just like electromagnetic spectrum. Okay. So here we can see different types of the rays, radio waves like this one, uh, infrared, ultraviolet rays, and this is the region, and X-rays. So region, ultraviolet rays and gamma rays. So in which just like this is the wavelength. It means 0.35 to 0.75, very small. So in which visible light will occur. You know that. Okay. So here also just like thermal radiation range is equal to 0.1 to 100 microns. 100 microns. Okay. So this is the ranges. So based upon the just like range of which one wavelengths, just like different types of rays will be occurred. This is the spectrum we already learned in physics. So here just like the propagation of thermal radiation takes place in the form of discrete quanta. It means thermal energy transferred in the form of the quantas. So each quanta, this is the formula for the quanta. So energy is equal to h nu. So you know this one. H is the uh, Planck's constant. We already learned in physics. So h value is equal to 6.625 into 10 to the power of minus 34 joule second. You know this one. Okay. So nu is the frequency. You know that value. Okay. So by so this is the photon energy. Then the energy is equal to, this is the formula. Okay. So now we'll see radiation. So radiation is nothing but so energy transfer across a system boundary due to the temperature difference. So temperature difference is the just a driving potential for the any mode of heat transfer. So you know that without temperature difference, heat transfer does not take place. You know that one. So this is the mechanism here. Just like we in conduction, we saw two types of mechanisms. So one is the lattice vibration and particle free electron movements. In convection, we saw the just uh, mechanism. It means movement of just like uh, particle movements. Particle movements occurs in two types. We already saw that by buoyancy effect, that is the free convection. By external agent, if it is particle movements occurred by some external agent, that is a forced convection of that. So here the mechanism for the radiation, for the transfer of heat from one body to another body, is the just like photon emission, electromagnetic wave emission, wave phenomena. Okay. So it means through electromagnetic waves, the energy transferred in the form of the photons. Okay. So all bodies radiant energy in the form of photons. So these are moving in the random direction. So with a random phase and frequency also. Okay. So just like when radiated photons reach another surface, suppose there are two bodies. So this is the emitting body, this is the receiving body. So just like heat energy takes place, transfer from the body 1 to body 2 by electromagnetic wave phenomena. It means in the form of photons. So just like energy, heat energy transfer from body 1 to body 2. So just like you can see, if the radiated photons reach another surface, they may be either here we will see three types of conditions. One is some energy will be absorbed, some may be reflected, some may be transmitted. So absorption and reflection and transmission is depend upon the type of material. Okay. So we'll see the behavior of, it means behavior of this surface. So here we'll see the behavior of this surface with radiation. So here three types of the uh, conditions. So absorption and reflection and transmission. Okay. So alpha, the letter just shows the absorptivity, and rho reflects the or shows the reflectivity, and tau shows the transmission parameter. Okay. So absorption means fraction of incident radiation absorbed. So just like this is the body, some portion will be absorbed, some portion will be transmitted, some portion will be reflected. Okay. So this ratio, these parameters depend upon the behavior of the surface. We will see those surfaces also. Okay. So first of all, we see the what is absorption. Absorption, uh, nothing but fraction of incident radiation absorbed. Similarly, reflectance means fraction of incident radiation, that is which is reflected. Okay. Fraction of incident radiation which is transmitted through the surface. We'll see. So thermal radiation is a volumetric phenomenon. Okay. So it means some opaque solids, will see, just like some surfaces. Opaque solids means just like metals. So the surface phenomena we can see, radiation emitted by the interior region never reaches the surface. So we'll see this condition, opaque bodies. The incident energy on a surface for unit area for unit time, so that is nothing but irradiation. Okay, how to remember that term? The incident energy on a surface per unit area per unit time, so that is called irradiation. So we'll see. So incident radiation, or Q, it is represented by G radiation. So G or Q. So it will be divided into three portions: Q R reflected, some portion; Q A absorption; Q transmission, some portion of energy will be absorbed, some portion will be reflected, some portion will be transmitted. Okay. So total Q is equal to so QA and Q reflection, QR and Q transmission. Okay. So we can see that one. So finally Q by Q is equal to QA by Q, QA by QR by Q, and Q2 by Q is equal to 1. So total is equal to 1. We can observe this one. So here, so incident radiation, most probably it will be divided into three portions. Okay. We'll see some just like first alpha, that shows the absorptivity. So that is nothing but fraction of irradiation, absorbed by the surface. Just like alpha is equal to QA by irradiation, it is G or Q. Okay, incident radiation. So absorption radiation by incident radiation. Okay. So alpha, that shows. So this value is always in between the 0 to 1. You know that. So rho is equal to reflectivity, the fraction of irradiation reflected by the surface. So rho is equal to QR by G. G is the incident radiation. So this one also varies between the 0 to 1. So third one is the transmissivity, tau. It is reflected by tau. So is equal to fraction of irradiation transmitted by body. Okay. So transmitted radiant by incident radiant. Okay. So total alpha plus rho plus tau is equal to QA by G and QR by G plus Q T by G. So total is equal to 1. You know that one. Okay. So now we'll see behavior of the just like surfaces. So we'll see ideal radiators. It means a ideal thermal radiator. Ideal means perfectly. Just that is nothing but a black body. A ideal thermal radiator is called a black body. So it means it has some properties. You know that the first one is the in black body means it absorbs the completely the just irradiation energy, radiation radiated emitting energy. So okay, so it completely absorbs. So it means alpha is equal to completely 1, remaining reflection and transmission. So it means and the rho and tau, so both parameters will be 0. Okay, if alpha is equal to, if the total irradiation or total instant radiation is absorbed by the surface, we can say that is the just like black body. Okay, so the condition for the black body is equal to absorption is equal to 1, so perfectly absorbs the energy. Okay, just like so for that one, for the black bodies, you know, the energy uh, radiated per unit area, the energy radiated per unit area, so it is represented by EB is equal to sigma T to the power of 4 according to the just like Stephen Boltzmann constant, Stephen Boltzmann law. Okay, so that is called just emittive or emissive power, the the amount of energy emitted by black body, so per unit time per unit area, so that is the EV is equal to sigma into T to the power of 4. So that is the just like overall energy emitted by black body. Okay, emissive power, so this is called it, EV is nothing but emissive power, so it absorbs perfectly and emits energy perfectly. Okay, so emissive power is equal to amount of energy emitted by black body per unit time per unit area. So according to Stephen Boltzmann, just like you already saw in first unit, so EB is equal to sigma T to the power of 4. Okay. So we'll see some types of another surfaces, just like here black body is nothing but alpha is equal to 1. It means uh, just like reflection and transmissivity both are 0. Okay, so white body just like which is opposite to the black body, in which just like reflectivity is equal to rho is equal to 1 and absorption is 0 and transmission also 0. So we can say if rho is equal to 1, we can say that is the white body. So in transparent bodies, just like glasses, so total energy is uh, transmitted. So okay, it means tau is equal to 1 and alpha is equal to 0 and rho is equal to 0. So just like we can classify bodies into three types. One is the black body and white body, transparent bodies. Okay, so also we'll see the opaque surfaces, opaque bodies, just like here, just like transmission, there is no transmission, just like tau is equal to 0 and the remaining portions, so some portion will be absorbed and some portion will be reflected. So alpha plus rho is equal to 1. So this type of bodies are called opaque bodies, just like metals. Okay, so we can say, so based upon the absorption and reflection and transmission, we can classify the bodies, just like black body completely absorbs and completely emits. Okay, so white body so completely reflects, transparent body completely transmitted, so the energy transmitted through that body, and opaque bodies only there is no transmission of uh, transparency, there is no transparency property. So it means energy does not transparent through this bodies, so only it absorbs or reflects. So those surfaces are called as opaque surfaces. So for the black body, so this is the just like formula for finding the emissive power. In order to emissive power is equal to amount of energy emitted by black bodies. So Stephen Boltzmann law for the black bodies. So that is the uh, EV is equal to sigma T to the power of 4. Now we'll see the emissivity. So what is emissivity? Ability of emission. Okay. So emissivity is the energy emitted per a surface to energy emitted by black body. So because black body is the perfect emitter, so remaining surfaces to comparison between the other surface to black body, because perfect emitter or perfect absorber is the black body. So here just like emissivity is nothing but it is represented by epsilon. So emissivity is equal to energy emitted from a surface by energy emitted by black surface at the same temperature. Both are at same temperature. So here just like we can observe one note, that is the, so for the Stephen Boltzmann law, it is useful for studying the overall energy emission. Overall energy emission, it gives EV is equal to sigma T to the power of 4 overall. So it does not gives the just like particular interactions, particular wavelength. Okay, just like we cannot measure the energy, emitting energy for a particular wavelength or particular interactions. Okay, so for that one, just like it is the just a drawback of Stephen Boltzmann law. So this problem was overcome by just like Planck's Max Planck's. So according to Max Planck, so he has also given the some formula to rectify those problem, and to find the emitting energy at particular wavelength. Okay, so we'll see in next class. In next class, we'll see the laws of just like different laws of radiation, just like Stephen Boltzmann law and Max Planck's law. So just like these types of laws we will see in next class. So just once again I'm repeating that one. Radiation is the third mode of heat transfer, you know that. So radiation is it is different mode compared to convection and conduction. Okay, so because in conduction and convection, so medium is very important, particle movements or particles vibration is very important. But in case of radiation, no need of medium, no need of the particles between the two bodies to transfer the heat. Okay, so without medium, so heat transfer takes place through electromagnetic phenomena. So that is nothing but radiation. So thank you for listening this class. We'll see in next class just different laws of radiation. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.